Okay, so welcome everybody. So we're very, very happy that you were able to come in Geneva. That's for the on-site participants. And of course, we welcome also our online participants who unfortunately couldn't come this time. So this Young Researchers Symposium will take place as a hybrid event. So there will be some audience, a lot of people here, as in this room and later in the other rooms, and there will be online participation as well. And the same for the speakers, for lecturers and speakers of this event. Roughly half of them will be on site and half of them will be online. So I welcome you on behalf of the local organizers, and I pass the word to Elise Raphael, who is the chairperson of this session.
Good morning to everyone on site, and hello, whatever time it is, to all the online attendees. So as Anton said, it's a great pleasure to welcome you all for the start of the Young Researchers Symposium 2021. Before I introduce our first speaker, I'd just like to make a few reminders concerning COVID-19 rules. So as you see in the room, you try to do your best to do 1 out of 2 chairs. We'll try to respect this rule as much as possible, even though we're allowed to fill 2/3 of each room. But please try to keep your distance as much as possible. Masks have to be worn at all time, except when you are seating to eat or drink something, so in the cafeteria area. Regarding the Wi-Fi, I already had a few questions. The UniGE guest is the one you should connect to, and it should be easy. If you have any trouble, you can ask any member of the staff. And yeah, if you have any trouble during this conference, any question, please come forward to any member of the staff wearing the burgundy t-shirts, and we'll help you gladly. That's all for the announcement for this morning. So I have the great pleasure to introduce the first mini course of these 3 days, and it will be by Martin Heyrer from Imperial College London. He will be telling us for 3 45-minute mini courses about Euclidean Yang-Mills theory. So Martin, here's to you.
It's not me.
Thanks a lot for the introduction. Well, thanks a lot for the organizers for inviting me. It's a pleasure to be here. Would have been even nicer if it was possible to come in person, but that was a bit complicated. And yes, I also wanted to say that because it's sad that Bonner joins thinking about something more. It would be nice to see him again. So the topic of the mini course is going to be Euclidean Yang-Mills theory, and so it doesn't matter if you don't know what the Mills theory is, so I'm going to try to explain that as one of the points. Maybe first I wanted to start by saying a few words of what the Euclidean here refers to. So it basically refers to Euclidean field theories as opposed to, well, Euclidean refers to Euclidean metric as opposed to Minkowski symmetry. And the setting for Euclidean field theory is basically that you have some space of fields. So the simplest case would be a field which is a function just from, say, Rd into R. But we'll see that, for example, in the case of Yang-Mills, fields are going to be a little bit more complicated, but generally speaking, they would be functions from some underlying space-time into some vector space in most cases, not necessarily. And then you have an action functional. And the action functional is just some function, say S, that goes from the space of fields into real numbers. And the sort of action functionals that we think about are typically sort of integrals over space of some Lagrangian density, which is a local function of the field. Right, so typically a local function, so the kind of example that you should have in mind, so that's the prototypical example would be S of phi equal to, say, the integral over Rd of gradient phi square plus V of phi. Okay. x here, just x, dx. And here it goes over the domain of which the field phi is defined. Right, so that's the prototypical example that you should have in mind. And then in principle, what one would like to do is one would like to construct a quantum field theory with this action functional. In particular, one would like to basically build some kind of Feynman part integral type theory. And that's typically quite hard. And so one way of achieving this is actually to do essentially some sort of Wick rotation, so you turn the Minkowskian space-time that you start with into Euclidean space-time, and basically what you try to build a measure typically on distributions given by e to the minus s of phi d phi, and some normalization constant here. And so the starting point here is that you have an action functional, which is something along these lines, and you want to use this to build a measure on a space of fields. But now typically your fields will not be functions, but they will actually be distributions. And this measure you want it to formally at least be given by a quantity like this. Essentially e to the minus this action functional times, and this here you should think of it as being something like your bag measure. And I put the back measure here in inverted quotes to remind you that there is no Lebesgue measure on any infinite dimensional space. Right? So the back measure, so what would a Lebesgue measure be in infinite dimensional space? It would be a measure, so a sigma finite measure, a proper measure in the sense of measure theory, which is invariant under all translations. Okay, so the Lebesgue measure on Rn is characterized by the fact that it's basically up to normalization. It's the unique measure which is invariant under all translations. And so in Rn this is well defined, but in infinite dimensional vector spaces, it's relatively easy to see that there cannot be any measure with that property, basically because there are too many directions in which you can translate, and that almost immediately contradicts sigma additivity. So this Lebesgue measure doesn't actually exist, and so that means that expressions like this are kind of problematic, and you need to think about how to interpret these. Then there is a procedure that once you have built such a measure, and it has a number of somehow nice properties, then you can actually go from there back to building an actual quantum field theory. Right? So in quantum field theory, you want a Hilbert space, a Hamiltonian evolution operator. You can build that from such a measure, and that was done basically by Savall and Schwaber back in the, I don't remember, it was exactly 60 or 70, so something like that. So this is a somewhat well-known procedure, if you want. So I'm not going to spend much time on this. I'm just going to take as that was just motivation. So in this case, we're just going to, ask ourselves the question of how, what are the tools that we have to build such a measure, and what does it mean, such a measure? So in the case of, for example, if your action functional was bilinear, so for example, if you take b equals 0, so if you remove the b here, and you only take this integral of phi squared, then this is a quadratic quadratic form. And then, of course, measures that are of the form e to the minus a quadratic form times Lebesgue, these are Gaussian measures. Right? And Gaussian measures do exist on infinite dimensional spaces, even if the Lebesgue measure doesn't exist. And we can, of course, quite easily guess. So, you know that if you have a Gaussian measure with covariance C, then it has density e to the minus x cx over 2. And so you can relate the operator that appears in this function. Also here, it's actually the Laplacian, right? So this can be written as, if you want, scalar product phi, Laplacian phi with a minus, and then plus the term with v. So here the operator that appears here in the quadratic form is the Laplacian, and so the Gaussian measure that this quadratic form would define is actually the Gaussian measure that has the Green's function of the Laplacian, so the inverse of the Laplacian as its covariance function, and that's usually called the free field. Okay, so there's at least one such example where you can easily at least interpret this expression, and that's the free case, right? When the action function is just given by this quadratic expression. But the interesting situations are the situations where the action function is not quadratic. Okay? And so in this mini course, I want to talk about Yang-Mills. And so Yang-Mills is what we call a gauge theory. And so before actually defining Yang-Mills, I want to just explain a little bit about gauge theories in general. So in gauge theories, the picture you should have in mind is that there is some underlying space-time. Okay, so that's, say, your RD. But then at every point of this underlying space-time, you actually attach a copy of some group. Okay, so this here, so you have some group G, which is called the structure group. And so you should think of basically replacing your space-time by space-time times copy of that structure group. Except that actually what you really do is so technical terms, you look at the principal bundle with structure group G. Informally, what this means is that you think of each copy of G here as being a copy of G, but where you forget which element is the identity element, right? So you think of, so G of course acts on itself, right? So there's an action of G on itself, which is GH, gets mapped to G times H. And so in this action, you should think of this copy of G as not knowing which element is the identity. As this copy of course does, right? Because here, if you put the identity element is the element, so that, you know, the transformation is trivial, the action here is trivial. But for the second copy of G, so the copy that G acts onto, which is what you think of this as being, for that one you think of forgetting which element is the identity, right? So if you want G, you could think of G as being like rotation, so in the simplest case where G is just a unit circle is U1, then you think of this G as just being a circle without specified origin, and the group of rotations of course acts on that circle by rotations. Right? And then you think of all the fields, so all the fields that appear they're always going to be of the form function from the RD times G into some vector space V, but so that V comes with an action of G. And the fields are always covariant in the sense that you only look at things so that f of, say, x hg is equal to h phi of xg. Okay, and that makes sense because phi is an element of V and G acts on V. So here h phi refers to the action of h on V. So of course, if you have a function with this property, it means that really, you know, if you know what it's worth, what the values are in RD, then you know the values everywhere, right? Because you just use that formula. So in some sense, it's really the same as just functions on RD, except for that thing that since we don't specify which element of G is, if you want, the identity, so which one is the preferred element, that means that here, of course, if I write it as RT times G, well, there is a canonical way of embedding RD into this, which is just by, you know, elements X, you map it onto X, comma identity, for example. But if you think of every copy of G here as not knowing which element is the identity, that means that you no longer have a canonical way of embedding RD into this. So the example that you can have in mind, right? So the simplest example in which these gauge theories somehow show up, and which you've actually already seen, all of you, even if you haven't seen it under that name, is if you look at electromagnetism in general, and in particular, actually, if you look at the evolution of a quantum mechanical particle in a magnetic field. Okay, so let me now just discuss that example. So the example is a quantum mechanical particle in a magnetic field. And remember, the magnetic field, I can write it as the curl of a vector potential A. And then your quantum mechanical particle is described by a wave function. So psi is a wave function that goes from R3, well, R times R3, because it depends on time, but at fixed time it goes from R3 into complex numbers. And it evolves by the Schrödinger equation, and the Schrödinger equation here is given by minus I gradient minus A square psi. Okay. Now, you know that in quantum mechanics, what is really observable is not the wave function itself, but you can observe basically, for example, its modulus square. Right? So the modulus square has the interpretation as the probability distribution of the location of your particle. Okay, so that has a physical meaning, but the phase shows up. The phase is important, because it influences the evolution here. But you know that in quantum mechanics, if you, for example, if you multiply the whole particle by a global phase, so if you multiply psi by just some unit element, you know, some e to the I theta in C, some element of modulus 1, that doesn't change anything. And it doesn't change anything observable at all. And But this is only if you multiply by a global phase, right? So in principle, if you multiply by a local phase, so if you multiply psi by some function e to the I chi psi, where chi is now a function, right? So if chi is a function from R3 into R, so if you do that, then in principle the equations of motion change. Right, so quantum mechanics is not that invariant on that. But actually, if you add a vector potential, or if you allow for magnetic field, then it turns out that it is actually kind of invariant under this, because what happens, so if I change psi into e to the I chi times psi, then basically it changes minus I gradient into minus I gradient plus gradient chi, right? Because when you hit psi with the gradient, then well, there's one term where the gradient just hits psi, and then there's one term where it hits e to the I chi, and so you have an I chi coming down, and if you multiply by minus I, that just gives you a plus one. So multiplying psi by some phase, some space-dependent phase, changes, if you want, the action of the gradient. But now I can change A as well. So I can change A into A minus gradient chi. And so if I do that, then, oh, okay, well, there's a minus sign here. Okay, so maybe it should be plus. So if I change A into A plus gradient chi, then you see that in this expression, well, this guy gets turned into minus I gradient plus gradient chi. This guy gets turned into A plus gradient chi, so these gradient chi's just cancel each other out. So it means that if I make this if I change A in this way, then the equation that's satisfied by the transformed psi is actually the same as the equation that's satisfied by the original psi. And the other thing we'll notice is that the curl of gradient chi is actually zero. Right? So the curl of a gradient is always zero. And so this keeps B unchanged. Right? So what you see here is that we can actually think now in the picture before, I can actually interpret psi, if you want, as a function of Rd times S1, where the Z here belongs to the unit circle. Again, with this such that psi of x e to the I theta z is equal to e to the I theta psi of x z. And you see that if I interpret psi in this way, then I don't need to specify, if you want, a choice of origin for the z. I can rotate independently all of these copies of the circle. That's precisely what this transformation does. Right? So now a transformation like this, I can view it as a change of coordinates. Right? So this transformation, I can view it as a change of coordinates on R3 times S1. Right? And so it's the change of coordinates which is given by xz is mapped to x e to the I chi of xz. Right, so doing that change of coordinate effectively is the same right? So if I interpret the psi's in this way, doing that change of coordinate is the same as performing that transformation on the psi in the original coordinate system. And so then, if we interpret the A itself, right, also, okay, we'll see in a second how we have to interpret the A, but so what we see here is that under these changes of coordinates, if provided that the A is an object that transforms in this particular way, and we'll see in a second how this forces us to interpret A. So if A is an object that transforms in this particular way under these types of changes of coordinates, then you see that our Schrödinger equation of a particle in a magnetic field is actually invariant under these types of strange changes of coordinates, right? So it's not a change of coordinate of the underlying space, it's a change of coordinate of that, the way that you attach a copy of the circle to every point of the space. And so this is what we call a gauge theory in general, right? So it's something which has that type of behavior. And so in this context, the space of functions, so here, this e to the I chi, or the function chi, so we call the space of transformation, the space of these coordinate transformations, the gauge group. So here the gauge group would just be functions from R3 to R, together with addition as a group operation, and they act on these functions in this way. Right, so this is a group action if you view this as a group element with pointwise addition in R. And so one maybe an important thing to realize here is that, okay, so I've shown you this interpretation, which maybe you've seen, maybe you haven't, of quantum mechanical particle in a magnetic field as a gauge theory. Now, you might say, well, okay, so it's maybe just some kind of fancy way of rewriting this. At the end of the day, this vector potential is really just some kind of trick in order to rewrite the magnetic field in a nicer way, but it doesn't really have much effect. But actually, there is an observable effect of A, in the sense that you can have a situation in which a particle moves entirely in a region in which the magnetic field is identically zero, and you can have an observable effect due to the fact that somewhere else the magnetic field is non-zero, but that region is never seen by the particle, and nevertheless it actually has a measurable effect. And that's the Aharonov-Bohm effect. So the setup here is that you have your particle and you run it into a beam splitter. So here you have a beam splitter. So now it has sort of 50% chance of going straight, 50% chance of getting reflected. And here you put a mirror. Here you put a mirror, particles that get reflected back. And then here you let it interfere with itself, and you put a detector here. So now what you do is you put a magnetic field here. Right, so here you have now a region with B non-zero. So you have the magnetic field sort of pointing, if you want, outside of the board. Now the particle, whatever it does, whether it goes straight or whether it gets reflected, it just doesn't see this region at all. But having b non-zero here forces A to be non-zero outside. Right? So in all of this region here, you actually have A non-zero. Right? So you can kind of figure out, basically you try to find a field so that the curl is basically a delta function, and you find that it has to be sort of non-zero outside. So you can describe your magnetic field by a vector potential, but the vector potential now is supposed to be non-zero outside. And if you look at sort of the effect that it has on the evolution of the particle, it actually has the effect of acting slightly differently on the phase of the particle that goes this way around compared to the phase of the particle that goes that way around.
Sorry, Martin, just a question. Is the... Can you hear me?
And so the effect here is that, well, by the time you get to the detector, you have the part of the waveform that goes this way around that interferes with the part that went that way around. And so depending on the strength of the magnetic field, you can actually have either constructive or destructive interference.
Sorry,
so
Martin.
You see an effect here on where you would actually detect the particle and where you would not detect the particle.
Sorry, Martin, just a question.
Yes.
Is this new definition of psi different from the one which views psi as a section on the complex line bundle or not?
Sorry, say again?
Someone is asking if the new definition of psi is different from the one which views psi as a section on the complex line bundle.
So here the psi, so it would always be, so psi here would always be, if you want, the section of the complex line bundle. So the psi, it doesn't matter, right? I mean, you can view it like that, or you can just view it as a function on R. It's completely equivalent, right? It doesn't make any difference. What I'm saying here is that the vector potential, which defines your magnetic field, does lead to observable effects, even though sort of classically you would think of just the magnetic field being the only thing that's observable, and so if your particle never enters if your equations are local and your particles never enters a region that has non-zero magnetic field, then you should not be able to actually observe anything about it. So that was the main point here.
Thanks.
So in general, so this was the example of a gauge theory where the structure group is just U1, right? So in this case, the structure group G is U1, so just the unit circle. And, well, okay, so that's abelian. So in general, it doesn't have to be, so in general, G can be any, let's say, any compact Lie group. And so the interpretation of A, so the vector potential here, in general, you should interpret A actually as a connection on this bundle. Okay. So what's a connection? A connection is essentially a way, so remember I told you that you should think of this bundle, you should think of these different copies of G as not having a preferred origin. And so this means that if I take a point somewhere on one of these copies of G, right, so then that projects down to some point of RD. Now I can take a curve on RD, right, so that's a curve on the underlying copy of RD, and I can ask myself, so is there a way of now lifting this to a curve on the Hurst space? So you would want to lift that curve to a curve on, if you want, RD times G. And then, of course, if I write it as RD times G, you would say, well, yeah, there's a natural way of lifting it, which is just, keep the G coordinate the same and just, move in the RD coordinate. Okay, so we just lift it kind of horizontally in this sense. But now again, I told you that, we should think of these copies of G as not having a preferred origin, and so we should think of everything as being sort of invariant under performing arbitrary rotations of these copies of G independently of each other. And so if I start to make arbitrary rotations, then of course what was horizontal before is no longer horizontal. Right? So it means I don't have a canonical notion of what it means for a curve to be horizontal. And so I need some structure which tells me how to lift a curve on RD into a horizontal curve on that bundle. And that's called a connection. Right? So a connection is basically a specification at every point here of, saying if I move in a certain direction in the underlying copy of RD down here, then how should I move in my bundle so that the curve should be interpreted, if you want, as the horizontal lift of the underlying curve here in RD. So the claim now is that actually the vector potential here for the magnetic field should be interpreted as a connection for this bundle, for this bundle. And so first, let's see if it's the correct type, right? So what should a connection do? A connection is if I tell you a direction in which I move in the underlying space. So here the underlying space is R3. So I tell you a direction of R3 in which I move. Then you have this copy of the circle at every point. And I should tell you now if I lift this curve to R3 times S1, how should I move in the S1 direction, right? So that means that basically for every R3 direction that I choose, every direction in the underlying space, I have to specify a direction of the tangent space of S1 in which I move in order to define my horizontal lift. Now the tangent space of S1 is just R at every point. It's canonically identified with R. And so that what I want is I want something that at every point of space takes a direction and spits out a number, and it should do this in a linear way. And so that's a one form. And of course, in 3 dimensions, one forms and vectors, if you write everything in coordinates, they all sort of look the same. So it turns out that if you think of how the vector potential should transform under changes of coordinates, you'll find that it should not transform like a vector, but it should transform like a form. Okay, so it is actually of the correct kind. So A is a one form, and so I can interpret it as a connection for R3 for this bundle here. So in general, for a gauge theory, I fix a compact Lie group which is an arbitrary finite dimensional compact Lie group. It doesn't have to be abelian. And I have a connection A and again, I just write it in coordinates, RB times G, which I think which I identify with is interpreted as a one-formed with values, right? So now at every point, if I give myself the direction of the underlying space, the direction in which I move, I have to tell you how you move on G, and so I have to give you an element of the tangent space of G at every point. And so an element of the tangent space of G is an element of the Lie algebra. So that's now one form with values in this Gothic G, which is the Lie algebra. That's associated to the Lie group G. And so now I have a natural notion of derivation, right? So now I have so let me draw a picture again. So I have the underlying, so let me draw the underlying D one-dimensional. And I draw again the G as the just U1, right? So I have these circles at every point. And so now if I take a curve, and I lift it, so I have a starting point here on the circle. So a curve, of course, on R1, I can't do many different curves, so I just have to go in a straight line. If I lift this, now at every point, A tells me which direction to move, so it might be lifted like something like this. So that now gives me a natural derivation, right? So if I have a function phi, which is any function from D into B, as before, or if you want, I can interpret it again as a covariant function, so I view it as a function of RD times G into B, which is covariant in the sense that multiplication with an element here is the same as multiplying with the same element here in B. And again, V comes with an action of G onto it. So now there's a natural way of differentiating phi in a direction which is sort of coordinate independent. Right? So now the natural way of differentiating phi which I write as Ti, say A phi at a point X. So now the natural way, so if I didn't have the group G, then of course differentiation would just be, you take phi of X plus epsilon I unit vector minus phi of X unit vector. You divide by epsilon, you take the limit as epsilon goes to 0. So here, this doesn't really make sense, right? Because this really means I start from the point X, I have to compare with the phi somewhere here, but I think of phi as being defined on this bundle, and so I have to move the point X to a nearby point, but the natural way of moving here, which is the coordinate-free way of moving, is given by the connection A, right? So the connection A tells me how to move in this space. Right? So the coordinate system doesn't tell me that. And so if I write this in coordinates, I find that this is basically e to the epsilon A. Right? AI actually. So if I move in the ith direction, that's AI, which tells me how to move. So this is the natural coordinate-free way of differentiating such a function phi. Right? So if you now do the calculation, you'll find that this is just, in coordinates again, it's just the partial derivative plus AI if you want acting on phi. And so now, one way you can, one calculation that you can do, which is quite instructive, but I think I'm sort of running out of time, so I'm maybe not going to do that calculation. But you can ask yourself, So the question, so if you want us to give this as a homework for tomorrow, because it's a very simple calculation, is how should one, so how should A transform under the action of the gauge group, right, or if you want, on the changes of coordinate. So that if you look at the covariant derivative of the transformed A acting on the transformed phi, and the transformed phi just means pointwise action, right? So now I have a G, which is a function from RD into capital G, so that's a coordinate transformation which acts by just pointwise multiplication, and we want this to be equal to G times EIA phi, right? And then well, the other exercise is convince yourself that this is, go back to the example of electromagnetism and see that this is indeed, in that particular example, that's how it should transform. Okay, so I think I'm going to stop here because I'm at the end of the 45 minutes, and then tomorrow I'm going to actually explain how Yang-Mills fits in this framework and what's the sort of things we can do.
Thanks a lot, Martin. I think we have time for a few short questions. If there is anyone in the room on site who wishes to ask a question, you can ask for the microphone. If there is anyone online, I will transmit the questions directly to Martin. Yes, there is one behind you, Roberto.
Can you hear me?
A bit louder, maybe.
Yeah, okay. So I would actually like to make a remark, if it's okay. Just because you mentioned this example of the Aharonov-Bohm effect, there's a paper from Gregory Moore, I think from already 2 or 3 years ago, so actually showed that in order to, you need to fix a Berry connection in order to do this, and this choice of Berry connection is actually also non-trivial and has some physics implication. I think it's interesting to mention that because this paper is quite unknown, but it maybe has some interesting physical implications beyond the usual detection of the non-trivial connection of that bundle. Yeah.
Okay, I didn't know that. Yeah. You can send me a link.
Yeah, sure.
There's just another question online. Luke says, I think you're saying that in the Aharonov-Bohm effect, you measure the holonomy of the connection around the region where the B field is non-zero. But during the whole path of the particle, the curvature is zero. So shouldn't there be zero holonomy?
So, yeah, but okay, the curvature, right, so the curvature is zero. The curvature is zero here, the curvature is not zero here. And so what you basically measure with the holonomy is sort of the integral of the curvature over this whole region, and it's not zero in here.
Okay, thanks. I think we won't have time for more questions, so I propose we thank Martin again, and we see him tomorrow. And we'll resume in 6 minutes.